Okay, so now we'll talk about square roots. And what a square root is, when you have a radical, yeah, the radical will have an index. The index, and it'll have a radicand. So we have an index and we have a radicand. And the index and the radicand are necessary numbers. Whenever you have a square root, we're implying that the index is 2. Whatever the radicand is, the index is 2. So you would read that the square root of a. But for square roots specifically, we've decided that you don't have to write the 2. So square roots, you don't have to write the index. So if you ever see a radical without an index, you can assume that the index is 2 and it's a square root. So square roots are radicals either with a 2 for the index or that don't have an index at all. On a number line, we have some known square roots. So let's see. We know the square root of 0. The square root of 0 is 0. Square root of 0 is 0. We know the square root of 1. We know the square root of 1 is 1. The square root of 4 we know is 2. The square root of 9 3. Square root of 16 is 4. Square root of 25 is 5. Square root of 36 is 6. Square root of 49 is 7. Oh, this is how these numbers fit onto a number line, right? So at those lattice points there, you have these perfect squares. 64 is 8 squared. 9 squared is 81, right? So these are perfect squares. These are all the perfect squares, and these are all of them in order all the way up to 141, which is 12 squared. So when you take the square root of those numbers, you always get integer values. You always get whole numbers. Those numbers are called the perfect squares. Those are special numbers. When the perfect squares are involved in a square root, the answer that you get will be a rational number, a number that you can count to, a countable number. So let's see. If you zoom in a little bit on this number line, we're missing some things. Like, for instance, between 1 and 2, for instance, between 1 and 2. So between the square root of 1, which is 1, and the square root of 4, which is 2. So between 1 and 2, the square root of 1 and the square root of 4, between there you have the square root of 2 and the square root of 3. Those numbers, the square roots are not going to give us whole numbers. They're not going to give us countable numbers. They're not numbers that you can count to. So the square root of 2 and the square root of 3, those are called irrational numbers. Those are numbers that are not countable. They're irrational. Unlike the black numbers here, the square root of 1. Oh, and here's another rational number, the square root of 4 over 9. You notice both 4 and 9 are perfect squares. The square root of 4 over 9 is actually rational and is equal to 2/3. That's a rational number. You can count to 2/3, 1/3, 2/3, 3/3, 4/3, 5/3. You can count by thirds, but you can't count by the square root of 2 or the square root of 3. You can't count up to that number. All right, let me see. We also have the square root of 5 and the square root of 6, square root of 7, square root of 8, all in the up in here. These are irrational, the red ones. The square root of 25 over 4. Well, the square root of 25 over 4 is just 5 over 2. So because that involves perfect squares, that's a rational number. That's 5 over 2, 2.5, 2.5. You can count by halves. All right, here we go. Here we have a bunch of irrational numbers in between here. There's some rational numbers too. Um, what I want to look at is I want to look at that one, the square root of 12. Let's take a look at the square root of 12, and this is what we've done in previous videos. The square root of 12, for instance, square root of 12 can be written in other forms. You can factor that into the square root of 4 times the square root of 3, or the square root of 2 times the square root of 6. But this is the one we're interested in because that's a rational factor. So we can break this up into the square root of 12 up into two parts. One factor that's actually rational, which is the square root of 4, 2, and the other one that's irrational, the square root of 3. So you can factor irrational numbers sometimes like that. Sometimes you can factor irrational numbers into rational factors multiplied by irrational factors like the 2 and the square root of 3 that we did there. Turns out there's another class of numbers that we want to look at here, and they involve this square root. This square root. So all the numbers that we had been discussing so far were all on a number line. But this kind of number doesn't fit on that same number line. Numbers involving the imaginary unit, I. So what's the difference? Well, both the red and the black numbers on this number line make up a set of numbers called the real number system. So the real number system, real numbers, are the numbers that go on the number line, and those numbers do not involve the square roots of negatives. You have negative square roots because the negative square root of 1 is just negative 1. That's just negative 1. And the negative square root of 2 is just, or square root of 4 is just negative 2. That's just negative 2. And obviously this is negative 3 and this is negative 4. But notice the negative, we're not taking the square root of a negative number. It's a negative square root. The whole square root is negative. On the other hand, whenever you're taking square roots of negative numbers, this factor is involved, this factor here. And those numbers don't fit onto that number line. If you were going to graph these, you'd have to make a separate number line. So the imaginary unit is used for the square roots of numbers like negative 1, as you can see. But then you can also use the imaginary unit, the square root of negative 1, to factor numbers like this one, the square root of negative 4. The square root of negative 4 would then factor into the square root of 4 times the square root of negative 1. And the square root of 4 is 2, and the square root of negative 1 is I. And it turns out that the square root of negative 4 is a number 2i. The number 2i won't fit on the real number line. You can't put the number 2i on the real number line here because it's an imaginary number. So you have the set of real numbers, and you have this other set of imaginary numbers where you count by I, the imaginary unit instead. You count by I, the imaginary unit. So let's take a look at some more here. Let's see. We could also have like the square root of negative 25. Square root of negative 25 would break down into, let me see, that's the square root of 25 times the square root of negative 1. And just like before, this would be 5i. That's an imaginary number, 5i. 5i. All right, let's try one more. Let's say I was looking for the square root of negative 24 in this case. Well, this one is a bit trickier, but one thing I know is that there is a square root of negative 1 here, which is where I'm going to get the I from. The I. But this other one, I can factor. Let me see. There's factorizations. I could try the square root of 2 and 12, but neither one of those is a perfect square, so I won't get a rational factor. I could try the square root of 3 and 8, but neither one of those is rational, so I won't get a rational factor. Or I could try the square root of 4 and 6. That works because the square root of 4 is a rational number. It's a known rational number. Square root of 4 is 2. The square root of 6 is just irrational, so you write it as the square root of 6. And I is the square root of negative 1. But we usually write it in this order: 2i square roots of 6. 2i square roots of 6. So this is also an imaginary number. This is also an imaginary number. Now, the way this works is usually if they're graphing these things, they'll have a real axis, which is a real number line, nothing involving I, and then they'll have an imaginary axis. So instead of the y-axis, they make this the imaginary axis, where we're counting by I here. So of course on this we have 1, 2, 3, and so forth. Negative 1, negative 2, negative 3, and so forth. But then we have the imaginary numbers here, which are I, 2i, which is the square root of negative 4, 3i, which is the square root of negative 9, 4i, which is the square root of negative 16, and of course down here you have negative I. Negative I is the negative square root of negative 1. That's equal to negative I. And then of course you have negative 2i, which is negative square root of negative 4. That's negative 2i. And then you have negative 3i, which is the negative square root of negative 9. That's negative 3i. So you have this real axis and you have this imaginary axis, where the real numbers go on the real axis and the imaginary numbers go on the imaginary axis. And then from this, it's kind of strange, you can get a different kind of number called a complex number. So there's also this bigger set of complex numbers. The set of complex numbers involves real numbers from the real number line being added to the imaginary numbers from the imaginary number line. So for instance, there would be this lattice point right here where the real number is 2 and the imaginary number is 3i, and that would be the point that represents the complex number 2 plus 3i. 2 plus 3i is in the set of what we call complex numbers. The set of complex numbers is an umbrella that contains all the real numbers from the real number line that we've been learning about, the rational numbers and the irrational numbers, like the black numbers and the red numbers from here. But it also contains non-real parts, imaginary parts. So the complex numbers are numbers like this here. All real numbers, 2 itself is a complex number. All imaginary numbers, 3i itself is a complex number. But the combination of the two, a real plus an imaginary, is neither fully real nor fully imaginary. It's in the set of complex numbers. The set of complex numbers, the complex number system. All right, so whenever you see the imaginary unit, the square root of negative 1, when you're taking square roots of negative numbers, then you have to make sure that you understand the distinction. You are no longer in the real number system on a regular number line. You are now in that imaginary number, on that imaginary number line, which is perpendicular here when you represent it to the real number line.